Guys, good morning. Shall we start? Is everyone ready? Right. So, if you can remember, I think we were talking about, I think last class we talked about collision theory, right? So, I told you how exactly collision theory works. It basically tells you how exactly a chemical reaction happens, right? So, in the form of collisions between reactant molecules, right? So, there were two conditions for the collision to be successful. Can you tell me what were they, guys? For a collision to be successful, there were two conditions which has to be satisfied. What were they? Hello.
The proper orientation and threshold energy.
Okay. So right. So the two conditions are: I should have proper orientation of the reactant molecules, and I should have some minimum energy possessed by the reactant molecules. Right. So those two are the conditions, and then I told you how an activated complex is going to get formed. That is the intermediate which is getting formed during the reaction, right? And then we saw the same thing in the form of a graph, right? So I told you the graph is what is called as the energy profile diagram. So if you can remember, the graph was something like this: potential energy and reaction coordinates, right? So the graph was something like this, correct? So this is where the reactants are there. That is, one second. So this is the point here. You see that the reactants are there. So this is the initial potential energy of the reactant, right? So the thing is, as the number of collisions increases, right? As the number of collisions increases, the potential energy of these reactant molecules will keep on increasing, right? So you can see that the potential energy of these molecules will keep on increasing, right? So now it is going to reach a maximum value, right? It is going to reach a maximum value, and that is where I say that the most unstable species is getting formed, and that is what is my activated complex, isn't it? So obviously this activated complex will have some energy, right? This activated complex will have some energy, and obviously this energy is what is called as my activation energy, EA, right? So once the activated complex is formed, it will start losing energy, right? And the product formation starts, right? So I told you, if I just divide this graph into two parts, right? So the maximum point is represented by the activated complex, right? So the point before that, that is the area before that, this area talks only about the reactant molecules, right? And obviously the product formation starts right after the activated complex. So you'll see that this particular area which I have here talks about the products. This area talks about the reactants, right? So we even saw one mathematical equation for all this, right? I told you there's something called as an Arrhenius equation, right? So Arrhenius equation was like this: K is equal to A e power minus EA by RT, right? So you can see that obviously if temperature increases, the rate of the reaction also increases, irrespective of whether it's going to be an exothermic or an endothermic reaction. That's what you need to understand, right? Generally, what comes to your mind is, say whether it's an endothermic or an exothermic chemical reaction, or say if it is endothermic, I understand that the reaction requires energy to be supplied for the reaction to happen, isn't it? Right. Say in exothermic chemical reaction, energy will be released along with the products. That we understand. So for an endothermic chemical reaction, if I increase temperature, the increase in rate is logical, isn't it? Because and already I require energy for the reaction to happen. I'm supplying more and more energy. So definitely for an endothermic chemical reaction, if temperature increases, rate obviously increases. We don't need to have logical this thing. It is purely logical, right? But for an exothermic chemical reaction, right, I am telling that generally, again, at least till certain point, till certain amount, if you supply some amount of energy, the rate of the reaction increases, right? Now, why is it happening? I will be able to explain that to you from the graph, right? Now, whatever the kind of reaction is, right? Whatever the kind of reaction is, initially the reactants will have some energy, right? So I told you this energy barrier which I have here, right? This energy barrier, that is the difference in energy between the potential energy of reactants and the activation energy. That is what is called as energy barrier, right? So this energy barrier has to be crossed no matter what, whether it's an exothermic chemical reaction or an endothermic chemical reaction. This energy barrier has to be crossed no matter what, isn't it? Right? So obviously, even for an exothermic chemical reaction, until certain point, right? Until certain point, increase in temperature will actually increase the rate of the reaction. Obviously, after that point, when the product formation starts, right? When the product formation starts, at that time, if you supply energy, yes, the rate of reaction is actually going to be the rate of the reaction is actually going to be decreasing. Understood, right? Fine. So from this energy profile diagram, I told you there can be a lot of information which you can get, right? Say for example, from this energy profile diagram, I will be able to predict whether that particular reaction is exothermic or endothermic. That is one thing. And second thing is, I will be able to check whether that particular reaction is going to be an elementary chemical reaction or a complex chemical reaction. Hope you remember what is elementary and complex, right? Elementary chemical reactions will happen in single step, one step process, like SN2, right? And your complex reactions are made up of multiple number of, say, simple steps, right? Multiple number of simple reactions, right? Okay. So that also can be found out, whether it's going to be a elementary chemical reaction or a complex reaction can also be found out. And one more thing, again, if it is a complex reaction, how many steps it takes for completion, right? How many steps it takes for completion, that also can be found out from the energy profile diagram, right? Or in other words, I will be able to speak about how many intermediates or how many transition states are there for that particular reaction. All these things can be found out from with the help of your energy profile diagram. Okay. So first we'll talk about how we'll be able to find whether that reaction is exothermic or endothermic. Okay, fine, cool. So from the energy, okay, say if I talk about endothermic reactions, right? If I speak about endothermic reactions, now what I understand from endothermic reactions, obviously we know that energy has to be supplied, right? Now, why energy has to be supplied, we can come to a logical conclusion, right? Say now, how can I put it is, the reactant molecules has to cross the energy barrier, right? The reactant molecules has to cross the energy barrier. That means they have to form the activated complex, which is having the activation energy, okay? Now, if it is an endothermic reaction, what I understand is, even though the number of collisions are there, even though the number of collisions keeps on increasing, that energy is not enough, right? That energy is not enough, right? And so that's for compensating that. So since the amount of energy obtained from the collisions are not enough, so obviously that's why I am supplying energy. I am supplying energy so that it reaches activated complex or it reaches the activation energy. Okay. So now how will the graph look? This is how the graph is going to look. If you can see, right? So initially the reactant molecules have very less energy, I would say, right? The reactant molecules are right. The reactant molecules are going to have very less energy, and that's why I'm supplying energy for these reactants, right? So you will see that from this point it is going to start, and obviously the energy of products are going to be greater, right? The energy of products are going to be greater than the energy of the reactants. Again, a simple explanation, isn't it? So for the reaction to happen, you are supplying energy, right? For the reaction to happen, you are supplying energy. That means for the reactants, the amount of energy is very, very less. So obviously the products will have more energy than the reactants. right? The product's potential energy is going to be more than the reactants. That is obvious here. Okay, so this is how the graph will look. That means the energy of the reactant, this is the energy of the reactant, ER, I'll call it, right, is definitely lesser than the energy of products. This is the energy of products, right? This is for an endothermic chemical reaction. Okay, fine. So now I think you can predict how the graph will look for an exothermic chemical reaction, isn't it? Right? You can understand that how the graph will look for an exothermic. Now, how will I go about it logically? Right. So the thing is, initially, okay, I know in exothermic chemical reaction, the reaction is going to give out energy. Right. Now, why is it giving out energy? Is that the reactant molecules initially had so much amount of energy, right? So much amount of energy that they can easily cross the energy barrier, right? And obviously, to bring in stability, lot of energy will be released. That's what we need to understand, right? Lot of energy has to be released. That's what we need to understand. Okay, so again I repeat, initially the reactant molecules have very high energy. Now this is exactly the opposite case of what we're seeing. In case of endothermic reaction, the energy of reactant molecules are very less, and that's why we are supplying energy, right? In that case, that is an exothermic case. Okay, so in exothermic case, the reactant molecules already have very high energy, right? The reactant molecules have already very high energy, so that's why you're seeing that the energy is coming along with products, right? So what do you see here? In this case, the exothermic chemical reaction, the energy of reactants will be higher than the energy of products, right? So you would have so if you have drawn the graph, you would have got a graph like this. So you can see the energy of reactants and energy of products. Here the energy of reactants is greater than the energy of products. In case of endothermic, the energy of products are greater than the energy of reactants. Again, you don't have to mug up anything. It's purely logical, right? So this is how, so you can see how from the help of from the graph, from the energy profile diagram, how will you be able to predict whether the reaction is going to be exothermic or endothermic? We will be able to see. Okay, fine. So this we explained, say, logically, right? So how will I prove it mathematically, right? So how will I prove that, okay, this graph is only for exothermic, this graph is only for endothermic, all that, how will I be able to prove, right? So for that, we are going to take a thermodynamic quantity, right? So hope all of you have learned about enthalpies of reactions, right? Or you have all learned about enthalpies of reaction, delta H, in your 11th class thermodynamics, right? So that value can actually be calculated from the graph, right? That value can actually be calculated from the graph. Okay, that we can do, right? Now tell me, how should be the value of delta H so that the reaction is endothermic or exothermic? How will you decide? Guys, did you understand my question? From the delta H value, not leave all this.
Negative means exothermic,
Delta
sir.
H is negative.
Positive means
endothermic.
endothermic.
Positive endothermic.
Good. So whenever you see that delta H is negative, that means it is endothermic, sorry, exothermic, right? And whenever you see delta H is positive, right, that means it is endothermic. Okay, right, fine. So now you would have studied this, that how will I calculate delta H for a reaction, right? How will I calculate the delta H for reaction? R represents the reaction, right? So you would have told like this, it is delta total enthalpy of products minus total enthalpy of reactants. It's as simple as that, right?
Yes.
Total enthalpy of products minus total enthalpy of reactants. Products minus reactants always, right? Okay, cool. So this total enthalpy of products and reactants are actually the potential energy. So this enthalpy, all these enthalpies are basically energy values. All these are, I know, is going to be in terms of kilojoules, correct, right? So these enthalpies I can actually speak about in the terms of their potential energies. That is, obviously, I know in y-axis I have potential energy. Here also I have potential energy. So with the help of the basically, so what I'm telling is the enthalpies are going to be equal to the potential energies of the reactant molecules and the product molecules, obviously. Okay, right. So now how will I be able to look at it? Now please understand, say for this graph, if I want to see what is the enthalpy, for example. Now I know it's a graph for exothermic, right? Okay, anyways, so we are doing the other way. With the help of enthalpy, we are predicting whether that reaction is exothermic or endothermic. Okay, so can I say initially this was the energy of the reactant molecules? Is it not? This was the energy of the reactant molecules.
Yes, sir.
Okay, and obviously if you look at the product side, this is the final energy of the products, final potential energy of the products. Okay, right. So now if I take, say, now this is say I give some value, this is EP. Okay, it's already there. Let me call it as EP, and let me call this value as ER. Okay, so now what will happen? It should be products minus reactants. Now which value is higher here? Look at this and tell me. Look at the graph and tell me.
Reactant.
EP is higher.
Yeah.
ER is obviously higher from the graph. I can tell that, isn't it? Look at this value and look at this value, right? So ER is definitely higher. So if I put EP minus ER, how will the value be?
Positive.
Hey,
Negative.
how is it possible? Negative, right? This is
Negative,
EP.
sir.
EP value is lesser
Okay.
and ER value is higher. Definitely this value is less than 0, indicating that it is going to be an exothermic chemical reaction. Okay, right? Now same thing we can do for this graph also, right? So if I do for this graph, again it's marked here, this value is what is my ER, that is the reactants of the energy of reactants, and obviously this value is what is the energy of products, right? Now if I look at here, same thing if I take for this graph, EP value is higher now, right? So EP minus ER, delta H is equal to EP minus ER. Now in this case, this value is going to be okay.
Positive.
Positive.
I think you're not. Yeah, positive. So obviously in this case, what I'm telling is EP minus ER. Now if I take this, obviously EP is higher, ER is lesser. So this value is definitely going to be positive. So delta H is greater than 0. So definitely it is going to be an endothermic chemical reaction. Right? So from the graph, actually, you will be able to see that. Okay, right. Now, one more thing also you'll be able to tell, right? So this is, you are talking about the absolute enthalpy, I would say absolute energies of reactants and products, right? Now, let me take a graph, let me take a reaction like this, okay? Say if I have a reaction like this, N2 plus 3H2 giving 2NH3, like the stoichiometric coefficient doesn't matter, but still it's writing, right? Formation of ammonia. I'm taking this reaction here, right? So I know this reaction is a reversible reaction, right? I know this reaction is a reversible reaction. That means ammonia can form nitrogen and hydrogen can form ammonia, isn't it? Right? Okay. So if that's the, again, like whatever the type of the reaction is, right, whether it's a reversible or irreversible or whatever the type of reaction is, the shape of the graph is not going to change, right? The shape, that again is going to be a dumbbell shaped graph. That's obvious. That is not going to change. Okay. So from say I'm going to say that there is going to be one forward reaction, there is going to be backward reaction. All these things are happening. Okay. So from this also I'll be able to tell whether the further reaction is exothermic or endothermic. Okay. So how will I be able to tell that? Is by looking at forward reaction separately and by looking at backward reaction separately. Okay, let me draw a new graph for you. Say, I don't know whether it's going to be endothermic. I'm just drawing some random graph. Bear with me. Okay, this was what I have. Okay, fine. So obviously, this particular curve, which I have here, if I can mark it, say until this point, is the activated complex, right? So can I say this particular graph, which I have here, talks about the forward reaction, right? Or say if this entire graph, if I take the arrow marks like this, if it goes like this, It talks about the forward reaction, right? That means this talks about the energy of N21H2. Okay, right. Now, if I come from that side, basically, I am going by this side. I'm going like this, right? Now, that talks about the backward reaction. That talks about the backward reaction. So, obviously, this graph that is from left to right, if I go, that is forward reaction, left to right, right? If I come from right to left, it is going to talk about the backward reaction. Obviously, right? Okay. So what I'm trying to tell is, you will be able to speak about enthalpy even in terms of activation energy of the forward and backward reaction. Right? Again, I'm telling you will be able to speak about the enthalpy of the reaction even with respect to the enthalpy of the forward reaction as well as the backward reaction. Okay. Now from the graph, we will try to locate what will be the activation energy for the forward and what will be the activation energy for the backward reaction. We'll try to do that. Okay. So now I already told you how the activation energy will look. So obviously this value, say this is the activated complex, that is the activation energy. I would say, okay, this is the activated complex. Okay, this particular thing which is forming here is what is my activated complex, right? So if I have to calculate from the graph what is the activation energy for the forward reaction, can I say this entire area, this entire length is what is my EA forward, that is EAF if I write, right? It is going to be activation, because from, I'm sorry. One second, guys, this is not the thing. Okay, it is actually this curve. Like this is the initial energy of the reactants. It has to cross the energy barrier. So this is my activation energy for the forward reaction. No problem. Okay. Now same thing if I have to do for the backward reaction, that is from left to right to left, from this, can I say this length, that is from the energy of the products to this. Now here products are going to act as the reactants because I'm talking about the backward reaction. Anyways, doesn't matter. So this would be the activation energy for the backward reaction. This would be the activation energy for the backward reaction. Okay. Now you already know how to calculate enthalpy, right? So from the graph, from the idea which you already know, so this particular value which I have here is what is my EP, and this particular value I have here is what is ER, right? And I told you delta H is going to be equal to EP minus, I'm sorry, this is ER, this is EP. I'm sorry, products, reactants, right? So EP minus ER, right? So in this case, you can see that okay, in this case, whatever. Okay, so this is what is the enthalpy value which we know. Okay, fine. Now next, if I look at the same thing, I'll be able, now this EP minus ER, where do you think it is going to come? This is the EP value and this is the ER value, right? So if I subtract them, can I say this particular length, is what is my delta H, right? This I'm not talking about the activation energies now. I'm just talking about from the graph itself. How do I calculate? I mean, with the help of energy of reactants and products, how do I calculate the enthalpy value? So I know this is the enthalpy of, enthalpy of products. This is the enthalpy of reactants. So if I subtract them, this is the curve with this is the length which I'm going to get. Okay. Now same thing can actually be done with the help of your EAF and EAB, right? Now I'll directly give you the answer, but check whether you're getting. Okay. Now this can also be written as EAF, that is activation energy for the forward reaction minus the activation energy for the backward reaction. This is another equation which will tell us, again, just to find out whether the reaction is what is that exothermic or endothermic. Okay. Now again, look at this. If I draw a new graph for you, marking everything again. Okay. So this was my EAF, and this was my EAB, right? And what was the enthalpy? Enthalpy was here. This value is what is my delta H, right? This particular length is what is my delta H. So obviously, if I write EAF minus EAB, or say EAB minus EAF, this value is going to be delta H, isn't it? If I subtract this from this or this from this, I will be getting the remaining area. So that is my delta H. Again, so obviously sign matters. So that's why we always say that it is EAF minus EAB. EAF minus EAB. Now logically, again speaking, coming back to exothermic and endothermic, right? So for an endothermic chemical reaction, what we said that obviously I have to supply a lot of energy for the reactant molecule to reach the activated complex, right? So obviously I can say that for an endothermic chemical reaction, right, the activation energy for the forward reaction is greater than the activation energy for the backward reaction, right? Obviously, then what will happen? Then can I say this delta H value will be greater than 0? If EAF is greater than EAB, delta H will be greater than 0. Correct? So obviously that is going to be endothermic reaction. For an exothermic chemical reaction, EAF is lesser than the backward activation energy. And you can see that obviously here in this case it is going to become negative. So if you calculate this, you can see that here EAB is bigger, EAF is smaller, right? So definitely that value is going to be negative, right? And obviously the reaction is going to be an exothermic chemical reaction. Okay, so either you speak in terms of energy of reactants and energy of products, or you speak in terms of activation energy for the forward reaction and the activation energy for the backward reaction. Either way, you will be able to calculate the enthalpy values and decide whether the reaction is going to be exothermic or endothermic. Okay, guys, any doubts? Everything is clear what we did here?
So yes, sir, can I just copy it down just a minute?
Yeah, sure. So the thing is, guys, there are so many people here. Everybody understood what is happening?
Yes, sir.
Yes, sir.
Yeah.
Okay, fine. Guys, my drawings would have been little shabby, right? So you can do a neat work, right? But all these things will not be there in your books, and questions also generally will not be asked. But again, these are all certain good stuffs to know, right? So I cannot teach you for marks. I teach you for chemistry, right?
Okay, sir. Thank you.
Okay, cool, right? So that is about how do you find whether it's going to be exothermic or endothermic, all these things. Okay, fine. Now we'll see whether we'll be able to find out the number of steps, right? Whether it's going to be an elementary reaction or a complex reaction. If it is a complex reaction, how many steps it is going to take? All these things can be again found out from the energy profile diagram. Okay, so we'll see how it goes. The best example I can take is SN1 and SN2, guys, which you have studied in your organic, right? Okay, so if I want to, first we'll talk about SN2 because I know it's a single step reaction because it's going to be an elementary reaction, right? So if I look at the mechanism, right, say some A, B, C, and say this is the leaving group, LG. Okay, this would have been the leaving group LG. Say now the nucleophile will come, right? Now the nucleophile is going to come from the back side. Hope you all remember. Right, from the back side it is going to come, right? So now what is going to happen? So I'm going to have an intermediate in which carbon is almost going to have 5 bonds, right? So how do I say 5 bonds? It's like this, A, B, C, and now this nucleophile and this leaving group are there. So what is represented by the two dotted lines which are here? You already know it, but still I'm telling. So it represents that simultaneously this bond is broken and this bond is formed. That is simultaneously the leaving group leaves and the nucleophile makes a bond with carbon atom. This happens simultaneously. So this is my basically the intermediate which is getting formed, right? And obviously as it will completely lose leaving group and the nucleophile would have been completely attached. And I know there is going to be inversion of configuration. All these things are going to happen. We'll not go into that. So you can see that this is the intermediate, right? So this intermediate is going to completely leave the leaving group and the nucleophile is going to get formed and the products. That's it. A single step. This is what we call it as single step. Okay. So please guys, please understand that there is a difference between the words transition state and intermediate. Okay, so let me write this down. But people use it like they use whatever they want at whenever time. So there's something called as transition state and intermediates. Okay, so in this case, I'll call this particular thing which is there, this one, I will be actually calling it as a transition state. Okay, so why is that? Is it because generally if I say organic chemistry intermediates, right? So tell me what are all the intermediates you know in organic chemistry, guys? What are all the different types of intermediates you know from organic?
I don't know, sir.
What? Now, if I tell you the
Sir,
names, then you will know. Okay.
it
These
can
are the
be
ah.
it can be a ketone group or something like that.
No. Those are substrates. Okay. So the thing is, so intermediates. If I tell you the answer now, then you'll okay. This is what are called as intermediates. So tell me. So the thing is, intermediates can be 4 or 3. I would say 3. Right? Carbocations, carbanions, and free radicals. These 3 only can be the intermediates. Do you know this? Did you know this?
Yes, sir. Yes, sir.
Yes.
Correct. So you know what is carbocation, you know what is a carbanion, you know what is a free radical, right? So all these are or what are called as organic intermediates. There's one more called as carbenes, but again, like for your level, it's not required. Anyways, right? So intermediates and transition state, the only difference is the transition state is highly unstable. Like you can see that this is highly unstable, isn't it? But intermediates are little more stable than intermediates. But again, intermediates are less stable than products. That is for sure. Well, please understand, when I talk about the stability of intermediates and stability of transition states, intermediates are more stable. Transition states are highly unstable, right? So this is what is my activated complex which is getting formed in the reaction. Basically, this one only will have the activation energy. So the transition states correspond to activated complex and they will have the activation energy, right? And in this case, there are no intermediates. There are no intermediates because it's a single step reaction, right? So let me put it like if you can see what's happening in SN1, you will be able to get a clear-cut idea between transition state and intermediates. For now, please understand that this is the intermediate. Sorry. This is the transition state. Okay, so now obviously the graph will just have just only one peak here. The graph will have only one peak, and this peak is indicated by this activated complex. Okay, right? Fine. Now let me look into the SN1 reaction. We'll see what happens there. Okay, so hope you remember what happens in SN1. There are two steps. Right. So here I have some A, some B, some C, and I have my leaving group. And say first, okay, basically the nucleophile, okay, in presence of the nucleophile. Okay, in presence of the nucleophile, what is going to happen? Now the leaving group leaves. Completely the leaving group leaves. Now, now see, the step, if I want to represent this, I will be able to represent it like this. A, B, C, and if I put a dotted line indicating that the leaving group is leaving, the bond is breaking. Okay, right? The bond is breaking. Right. So now this is my first transition state. This is my first transition state. Okay. Now, obviously, at the end of this step, the entire leaving group would have been gone. The bond would have been completely broken. What will be left with? You will be left with A, B, C with a carbocation. A, B, C, that is the three groups with the carbocation is getting formed. This is what happens in your SN1 reaction, right? Now, this is my intermediate. The carbocation is going to be my intermediate. So obviously, if you think about the stability of this and this, definitely carbocations are more stable than the transition state. Okay, so again, this will continue. Now what will happen? I will have the nucleophile coming, right? This nucleophile is going to attack the carbocation. So you will have A, B, C. Now again, I'll represent it with the help of a dotted line, nucleophile. Right? So again, this particular thing which I have here is my second transition state. Second transition state. Right? Then what will happen? This bond would have been completely formed, or okay, I'll write it here. Right? So this bond would have been completely formed. A, B, C, and the nucleophile. Bond is completely formed, and this is my products. That's it, right? So let me give you a very quick idea of what happened here. So I had the normal, that is the reactant. So in the presence of the nucleophile, the leaving group is leaving, right? So I represent that with the help of a dotted line, right? So this is my first transition state. TS represents transition state, and this leaving group would have completely gone. You end up with a carbocation. This is my intermediate. So if you look at the difference, what is happening here between the transition state and the intermediate here? Okay, then what is going to happen? After to this, the nucleophile is going to attack. So you will see that the nucleophile C bond is going to get formed. Again, I represent with the help of a dotted line. So again, this is my second transition state, right? Then what is going to happen? The bond would have been completely formed. So this would have been my product. Right. So guys, did you understand the difference between the intermediate and the transition state here?
Yes, sir.
Guys?
Yes, sir.
Okay, so everybody understood the difference between the transition state. Basically, transition state is the state between the intermediate and the reactants, I would say. That is in between state, right? Now, how the graph is going to look, how the energy profile diagram is going to look for this particular reaction. If you see, you first take this down, I'll tell you. Okay, hope you have taken this down. Right, can I wrap this part, guys?
Yes, sir.
Yes, sir.
Okay, cool, thank you. So now looking at how the energy profile diagram will look. So if at all you have predicted, I don't know what you expect. So this is how I expect the graph. Makes sense, right? Isn't it? So do you see that for an SN2, you got something like this. This indicates that there is only one transition state. This is for SN2, right? But for SN1, you know there are going to be two transition states. So this is the first transition state. This is the second transition state. So where is the intermediate then? The intermediate is here. This is my intermediate. That is my carbocation. So obviously I told you, you know how energy and stability are related, right? High energy, less stability. Energy and stability are inversely related. So you can see, obviously compared to the transition states here, the intermediates are having lesser energy, indicating that intermediates are more stable than the transition states. Are you able to get what I'm saying, guys? Right? So what you can understand is, I told you whether I'll be able to decide whether the reaction is going to be elementary reaction or a complex reaction. So if you see only one peak like this, if you see only one peak like this, then it is definitely going to be an elementary reaction, right? If you see more than one peaks like this, say so many number of peaks you see, right? And those are going to be complex reactions. And obviously the number of peaks you see in a complex reaction is going to be equal. This is going to be equal to the number of steps that reaction takes. Obviously in SN1, I know it's a two-step reaction. So you see two peaks. If there's something like you have a three-step reaction, then you will have three peaks, right? And number of peaks also talk about the number of transition states, right? And number of peaks, and I can also say number of peaks minus one. Number of peaks minus one is going to give me the number of intermediates. So you can see there are two peaks, one intermediate. So total number of peaks minus one is going to give me the number of intermediates. So all these things can be calculated. All these things, whether it's what is that, elementary or complex. If it is complex, how many steps, how many intermediates, how many transition states. Lot of information can be got from this energy profile diagram. Okay, right? So again, all these are not there in your textbooks. It will not be there, I guess, right? But anyways, it's good to know. You're studying something. It's very just a little higher, Okay, fine. So that's about elementary and complex reactions, right? Cool. So now what we'll do is, these are the things which we'll be able to study, whether it's exothermic or endothermic, whether it's elementary or complex, all these things, right? Whether the reaction is forward reaction is favorable or the backward reaction is favorable, all these things can be calculated, right? Cool. So we'll move on. We'll move on to Arrhenius equation. We'll try to mathematically modify it, guys. So guys, any doubts here? Is everything okay?
Yes, sir.
Yes, sir.
Okay,
Yes, sir.
cool. Right. So we saw Arrhenius equation was like this: K equal to A into e power minus dA by RT. Right. So like if I what I'm saying is, so if I increase temperature, right? If I increase temperature, definitely the K value is going to increase. From the mathematics, you can see that it's e power minus is there, and I have 1 by t here, right? So obviously minus and 1 by t indicates that it is e power some power of plus t. That's how it is. So obviously if temperature increases, the rate of reaction increases. That is done. Okay. So now obviously if I say this is a temperature T1, right? At temperature T1, I will have K1. Okay. So at temperature T2, I will have K2. A is the constant, activation energy is the constant, RT2. Okay. Now I'll be able to get a beautiful equation between the relationship between T2, T1 and K1 and K2. I'll be able to get an equation, but not in this form, but in the logarithmic form of this, because I have e powers and all. I don't want to work with it. Log is a little easier. Okay. So this equation, let me convert it like this. I can convert it as log of K1 is equal to log of A plus, or minus is there, minus 2.303, sorry, 2.303 EA by RT1. Can I write it like this? Right. So obviously now what I did here, I have log of two components. So log A plus something will come, log A plus again y again. So you can see that log and e power x, log of e power x, if I write, what does it come? X, right? Because my log and my exponential are inverse functions. Hope you know what is inverse function. Sine, sine inverse, tan, tan inverse, right? So log and exponential are inverse functions. So if you apply both of them together to a particular variable, only that variable comes out, right? So the same thing happens here. Log of e power something. So log and e power will get cancelled. So you'll have only this, and this 2.303 why I'm writing, because it will be in base of ln. Log to the base e will be there. So to convert it, I just multiplied throughout by 2.303. Right? So this only would have happened. Okay, right? So the same thing can be done for your second equation also. So I have log of K2 will be equal to log A minus 2.303 EA by R T2. Again, R is a constant, EA is a constant, A is a constant. So only temperature and the K values are varying. Okay. Cool. Now what I'm going to do is, say if I call it as 2, and this if I call it as 1, I'm going to take 2 minus 1. 2 minus 1 I'm going to take. So now log K2 minus log of K1 will become log K2 by K1. Can I say it like that?
Yes, sir.
Right? K2 log K2 minus log K1 will become log of K2 by K1. Log A gets cancelled. Right? So I have minus 2.303 EA by R common. Here also minus 2.303 EA by R common. Right? And it is, okay, let me write the full equation itself. So you'll get log K2 by K1 is equal to 2.303 EA by R into 1 by T1 minus 1 by T2. So basically it should have been 1 by T2 minus 1 by T1, but I have just taken multiplied the negative sign inside, right? So it would have been 1 by T1 minus 1 by T2. So it is 2.303. Am I doing everything correctly? EA by R into 1 by T1 into, okay, correct. So this is the equation. So again, if I little rewrite it, so just converting this, I have log, guys, I did a very small mistake. This 2.303 has to come in the denominator. So this would have been EA by 2.303 RT1 so this would have been EA divided by 2.303 RT2, and this again EA by 2.303R. I'm sorry. I just change it, right? So now the beautiful equation comes out. Log of K2 by K1 is equal to EA by 2.303R into T2 minus T1 by T1 into T2. This is the equation which we have to work with. So if two temperatures are given, say they'll say that at this temperature the constant was this much, and then on the next temperature find out the K value, and they will give you the activation energy and all that. Please remember, R value here is 8.314, because we're talking in terms of joules. Activation energy will be in terms of joules, right? So obviously your R value should be 8.314. Okay, cool. Anything else which I have to say? I have to do a lot of problems, obviously. But if I do some graph, like if I plot a graph between log K and 1 by T. Okay, so I have log K and 1 by T graph. Can you tell me how the graph will look? I'm not talking about K1, T1, K2, T2. I'm just asking log K, rate constant, log of rate constant versus 1 by temperature.
Straight line.
Okay, good. Straight line. Can you tell me whether it will pass through origin?
Yes, sir.
Yes, sir.
Will pass through origin. Okay, fine. What is the slope? Okay, first, whether it will have a positive slope or a negative slope.
Positive.
Okay. Okay. Hope you've taken this down, or even if you don't have, just take down the final this thing. It's very simple, right? Okay. So you had K equal to A e power minus EA by RT. So if I just take log on both sides, right? So I can write it as log K is equal to log A minus, say if I write 2.303 also, so it will be minus EA by 2.303 R into 1 by T. Can I write it like this? Okay, so this is my y-axis and this is my x-axis. Okay, so this is equal to y is equal to C, this is my C minus M into X. So this is my minus M, this is my slope. EA by 2.303 R is would have been my slope, and I would have had some intercept also with a negative slope. So the graph would have been like this. This would have been the graph. Y is equal to mx plus c. Here I have a negative slope, right? So obviously I can say that this intercept value is what is my log A, right? And the slope of this line is basically minus EA by 2.303 R. You can see EA by 2.303 R is what is my slope, minus I indicate. Okay, so from the graph also sometimes 1 marks and all can come, right? So the graph is a little important, right? Log K versus 1 by T graph, straight line with a negative slope of EA by 2.393 R, and the intercept is going to be log A. Okay, fine. So next class, people, we'll be doing a lot of problems on this Arrhenius equation, right? And one more thing also I'll tell you next class, if I have catalysts, right? I know catalysts are going to increase the rate of the reaction, right, by doing something. So we'll see what are they doing and how are they able to maximize the rate of the reaction, again with the help of the energy profile diagram only, right? From the energy profile diagram there is going to be some changes in the graph, right? Thereby the reaction becomes faster. So just like how you had a modification in the equation of Arrhenius when I have different temperatures. So I can even have a modification of the Arrhenius equation when I have catalyst and when I don't have catalyst. So again, I can get a correlation between those two situations. So all these can be done, right? So I hope you learned a lot of things today. Okay, so until next class, we'll see you again. Bye bye. Thank you.
Thank you, sir.
Thank you. Thank you.
Thank you, sir.